I guess, welcome to this evening talk. We are really very pleased to have two speakers who are really well known, and this is a topic that we haven't had a talk in a while in SECED, and so we were very excited when they offered to present this in front of the audience. As far as I know, there is no emergency fire drill scheduled today, so in case if there is a fire alarm, then we will all have to walk out of the room and we will be guided to our emergency procedure and follow the emergency procedure. So let me just introduce the speaker. As you can see, the title of this is Aircraft Impact Hazard for Nuclear Facilities. How certain are we? And just to introduce the speakers, we are pleased to have Richard Fowler. Richard is the Nuclear Safety Inspector, Civil Engineering. He's an earthquake engineer. He's already earthquake engineer working for the Office for Nuclear Regulation as a principal inspector, nuclear safety within the civil engineering and external hazard specialism. He has been with the ONR since 2013 and has been working within the nuclear industry for over 20 years. He continues to lead the ONR assessment of seismic hazard work for new build projects and operating facilities, and is also involved with generic design assessment. And also I also would like to introduce my colleague, Dr. Ming Tan. Ming is the Technical Excellence Lead for the Nuclear Division at Mott MacDonald. He has a PhD in Structural Dynamics. Ming is the Technical Excellence Lead for Nuclear in Mott MacDonald, responsible for driving the technical and innovation strategies in the nuclear sector within Mott MacDonald. Before that, Ming was the Advanced Analysis Discipline Lead, responsible for the direction and management of Advanced Analysis team within the Mott MacDonald's Nuclear Division. The team has a wide range of skills, including complex finite element and explicit analysis, such as aircraft impact and nonlinear advanced seismic soil structure interaction analysis and design. Ming has been working in the nuclear industry exclusively for over 20 years, with the last 10 years focusing on nuclear new builds. Ming has extensive experience in the generic design assessment process and understands the challenges faced by various technology vendors going through the process, especially when facing the UK non-prescribed regulatory expectation. Ming is the current elected committee member for SECED for the last 7 years, and Ming has been a colleague for equally more than 10 years now. So I would ask Richard and Ming to please start the presentation.
Thank you for those introductions. So what I'm going to do here is really provide a bit of background, the setting, because ultimately this is an ONR funded piece of research. The formula that the slides are going to follow is just present the background, the scope, and importantly the why, because this has not seen much light of day for a while, so that we'll touch on that. After which we're going to start examining the technical content and ultimately the conclusions of the research. Okay, so I thought I'd start by just outlining, for those I know many here will know, but some of you might not, the Office of Nuclear Regulation. So we are the UK's independent nuclear regulator for safety, security and safeguards. And we have 5 statutory purposes to ensure safe nuclear operations now and in the long term. And these relate to nuclear safety, nuclear site health and safety, nuclear security, nuclear safeguards, and safety and transport of nuclear and radioactive materials. And ONR has the legal authority to regulate nuclear safety, nuclear security and conventional health and safety at the 35 licensed nuclear sites in Great Britain. So that's us as a regulator. Now this you may not be as aware of is with the introduction of the Energy Act, we are empowered to conduct research. Now clause 88 of chapter 3, it says this, quite interesting: the ONR may carry out research in connection with the ONR's purposes or arrange for such research to be carried out on its behalf. When appropriate to do so, the ONR will publish those results or arrange them to be published. And we implement our research via our research strategy, which is available on our website. The work gets typically let via the the technical support framework which we have in place. So that's a bit of useful background. I think one of the questions that follows is then what would drive the regulator to actually commission a piece of research. And there's three areas or drivers they're called, and they're laid out here. O&R requires independent advice to assist with our decision making. That could be one. O&R has identified a knowledge gap which requires research, and or the specialists within O&R require greater understanding and oversight of developing innovations or emerging subjects. And it was felt that this research being presented today for aircraft impact touched upon all three of those drivers. So expanding upon that a bit more, the why, or the rationale behind why, it's important just to go over the current position. So we have our safety assessment principles, and they identify aircraft impact as an external hazard. We've got expectations within the technical assessment guidance, which is tag 13 in Annex 4 for aircraft impact. And duty holders are expected to consider both accidental and malicious aircraft impact within safety cases. Now the diagram on the right there attempts to illustrate a typical framework by which a duty holder may consider accidental aircraft impact. And you can see it follows those steps of identifying the hazard, determining a predicted frequency, applying a screening criteria, then ultimately at that point the hazard will be either screened in and a design basis established or screened out. But importantly, malicious aircraft impact is different, because with malicious aircraft impact we assume it can occur. Okay. So therefore threat definitions do need to be established by the duty holder, and we work in close collaboration with that. We have expectations as a regulator which we pass on to help get to that position. Okay, so that's where we have been, where we are. Some other peripheral factors which are significant to why this research was necessary is laid out in the next two slides. Malicious aircraft impact often dictates the design of civil structures for new nuclear facilities. I think we can all agree that it certainly does that, particularly reactor shells and other safety critical buildings or facilities. So it follows, overly conservative threat definitions could result in significant cost consequences due to increased construction costs for new builds or existing facilities, lots of extensive safety reviews. Conversely, underestimation of the threat definition could have safety implications also. Now, the significance of each of the variables related to that threat definition, and there are many, Ming's going to be touching on these, some examples given here: velocity, angle, fuel load, cargo, etc., has not been explored quantitatively, especially combinations of these different parameters. And that was something which on review was coming clear. So ultimately what mattered was not well enough understood. Unlike seismic, there was little guidance and references on this topic. Compounding the issue, analyses is typically complex, time-consuming and costly. And perhaps to conclude, one of the significant things was our O&R's regulatory expectations for malicious aircraft impact were last developed post 9/11 and have not seen any significant attention since then. And there's been a significant amount of work and development in the area which which led to really it being highlighted as a research need. So what will the research do? Well, the output is going to be used to inform a revalidation of the regulatory position. So this is the expectations that will get communicated to duty holders. So it's going to inform and provide the evidential basis for us to be able to do that. Okay, so that was the rationale for why. So how do we go about commissioning and splitting it up into some logical sequence of activities? Well, we commissioned the research via Mott MacDonald. Now, there's an important point to note here is that for us as a regulator, what we really wanted to achieve here was not just the view of one particular consultant or one particular branch of individuals. What we really wanted to do was establish what a consensus position was. So although Mott have been leading this work to add that robustness to the output, we had a peer review team established, and Ming will outline the composition of that, but essentially we had representation from Arab and also from specialists from outside of the UK. The research was split into two phases. Phase one was to provide ONR with an improved understanding of the sensitivity of aircraft impact load time functions to credible variations of the hazard definition and the significance of aircraft impact parameters to the definition of the hazard. It's kind of an exploration stage. And then phase two was to provide ONR with updated recommendations for representative threats that are relevant to the UK context using statistical analysis and other components as well, bringing that all together. And then the last but very important aspect was to identify the potential consequences for typical nuclear plant and nuclear facility protective structures under these postulated aircraft impact threats. The reason being is because we wanted to understand how much it would matter, what the consequence of changing threat definitions would be. Okay, so that's a flavour. Hopefully set the scene, and that's really all I'm doing because the main technical detail is going to now be provided in the following slides. There's just one caveat which I will note is that some of the there's a lot of detail in there, but there's a lot more detail which we cannot portray in the slides, and the reason is due to the sensitivity of the information. Okay, so if you see an area that Ming presents and you think, well, that's where's the results or where's this, it's that's the reason. So we've got to be very careful what we can actually put into the open public domain. Okay, so yeah, pleasure to hand over to Dr. Ming Tang.
Thank you, Richard. Before I proceed with the next 40 minutes of my presentation, I just want to highlight actually what I'm presenting today is not my work alone. It's actually a very large team of people that's undertaking this work. There's actually about 3 years worth of work done over two phases, as Richard was saying. And I'm the project director and framework director for this, providing the directions and providing the tools and support they need. But the real brains and of the piece of work actually come from the team. We have engineers, we have structure analysts, we have aviation specialists in there, also have safety case people. So the credits should go to them. I'm merely the conveyor of the information here, provide a summary of the work. And before the other thing as well, I suppose I want to add for that, from the project team perspective, we want to say thank you to ONR because the team have a really good fun in the last 3 years doing this work and doing some really exciting and interesting research work in here. And before I go into the details of research, I think the good thing is to provide a summary of the current status quo of aircraft impact assessment, what we're doing these days, and how we got to where we are today. For people who don't know, this is a brief from a historical context perspective. We started aircraft impact analysis as a load cases in nuclear power plants in 1968. 3 Mile Island, you've probably heard of that. And the main reason for that is because the power station is located very near the airport. And then if you work in aircraft impact assessment before, I'm sure you heard of Professor Rera. That's also when he developed the very famous Rera's function or load time functions. And then it's still been used up until today. And in the 1970s, there basically two main trends were formed. You have a commercial aircraft, which is generally dismissed unless there's an airport nearby, such as 3 Mile Island, and the combat aircraft, the fighter jets in this case, which is being used as a design case. One of the reasons for that is in the 1960s and 1970s, we're still in the middle of Cold War, and actually jet fighter at the time is still quite new, it's still a new technology. There's a surprisingly high level of accident rate for combat aircraft at the time. And in Germany, especially in West Germany at the time, there is a Star fighter, which is a small fighter jet, have an unfortunate nickname by the media as the Widowmaker, because there's a very high level of accidents of that aircraft. And Phantom F4 at the time is the largest available fighter jets and been selected as the load cases for nuclear power station and been continually used throughout the world until today. Of course, I'm sure we all know September 11 changes everything. We now know commercial aircraft is real and the consequence is very, very significant. And the conflict of Ukraine and all the other wars also, this become a real and present issues. However, I think it's worth highlighting that during the September 11, we have World Trade Centers, we have Pentagons, but if you put that next to a nuclear power station, especially the containment building and the spent fuel pool, it's actually the nuclear facilities are very, very small, even though you look at their huge buildings. But by no means that aircraft impact onto those facilities is impossible. In fact, in the last, before COVID, there's actually a detailed study done by the Switzerland, of which retired pilots was hired in a aircraft flight simulators to work out it is very possible for this to happen. And to add to that, you probably realize that there's actually a lot of aircraft in the sky. Of course, it's not to scale, but there's still a lot of them. And there's actually two important things to highlight in here. You've probably seen there's a little hole in Paris. You wonder why. Because this is actually taken on the 26th of July this year. That's the opening ceremony of the Paris Olympic, which you have the no-fly zones. The other big gap as well on the right-hand side is Ukraine and Belarus. I don't need to explain why there's not much flights in there. So we know it's real. There's lots of flights around it. What are the guides? As Richard pointed out earlier, there's not many. These are what I listed here. Those are majority of the guidance already available. And that's pretty much it. The three most useful one is the safety IAEA safety reports 86, 87, 88, and they're quite new as well, and there are lots of details in it. The problem though is even all these documents, even within IAEA, the information sometimes is contradictory. So they're telling you different things. What do you do? And the other probably most important, most used guidance is the NEI 0713, which set out the performance requirement and used heavily in the US. And I also want to provide a very high-level summary, a typical workflow, what we do in aircraft impact assessment. You start from the very top, in top left, you define the threats, the hazards, like what Richard was saying. That is the job of the regulator. And then you identify the performance level. And this could be based on your safety assessment principle, your radiological releases, limits, and things like that. Again, that is job to regulator to say, this is what we expect you to see. Some regulators will also tell you what the load time function, the load derivation is. In the UK, we don't. And some regulators even tell you what are the acceptance criteria you should be working towards. This could be your containment remain intact, your core cooling remains, and all this. Others, you have to rely on the duty holder have to define what are the acceptance criteria. Once you have this acceptance criteria, you then move on to determine your protection strategy. This is basically what you're trying to do here is define which building you need to protect and why. This could be because of your number of safety trains. For example, you could have multiple control rooms, could have multiple backup diesel generators, so only one will be taken out at a time. So protection, screening, shadowings, and all these different techniques. And then you basically down select into 1, 2, maybe up to 3 buildings that must be protected by the aircraft from aircraft impact perspective. This will always be the reactor building, but it could also be a building that consists of your span fuel pool or your control room. With that information, you can then work out your engine criteria. Typically, it would be there's no penetration, the aircraft would not get in, or it could be no scabbing, or it could be, and then you define your strain limits and your rotations, etc. in this case. Once you have those information, you then go back to the left, or your load derivation, your load time functions, you define your characteristic. That is where there's some characteristics that is defined by the regulator, such as your impact, what type of aircraft, your impact, even impact angle, impact velocity, but some is completely a duty holder's responsibility. For example, your impact scenarios, etc. Then you can analyze it. There's two main ways of analyzing it. You could use the classic load time functions approach. You could use what we call MTI, is the missile target interaction approach. Then basically you do all your fancy analysis, and you then make a check, undertake the design or assessment to make sure you meet what you set out engine criteria to. Then you may require enhancement, or you confirm you meet the acceptance criteria. That's how the whole aircraft impact safety case has been built up. But as you can see, this analysis usually takes a lot of time and a lot of effort, but the important part is actually what input you are going into, which is what we're discussing here today. So this is the area, the circle area, is where we focus on today, is what are the threats and what sort of characteristic in the threats we should be using. But before I go into that, I want to briefly use 2 or 3 slides to explain the various techniques for load time function, for the load time function approach and the missile target interaction approach. So there, as I said, there are 2 main approaches: load time function approach and the missile target interaction. And load time function approach itself have 2 ways. You have your classic rear function, which essentially convert the whole aircraft into essentially multiple degree of freedom systems, have crushing zones and things, and crushing and very clever approach and very computationally efficient. Or you can do a more detailed finite element load time function approach. Essentially, you build an aircraft model, you crush onto a rigid wall, you take the reactions. You should come up with a very similar answer to radius function if you do everything correctly. And then, of course, you also miss the missile target interaction, which usually is explicit, and that would then require modeling of the target itself, and the size and the rigidity of the target will affect the results. Essentially, one is a couple approach, one is a decouple approach. And then I'm not going to go through the details on the benefits of radius function and benefits of finite element analysis, but in a big handful manner, is radius function is quick, simple, very good in combat aircraft, but not so good in commercial aircraft. Also, especially when you have oblique impact, especially when you have complex geometry, and also if you have a target that's much smaller than your aircraft. So your aircraft, if you to do just your radar function, you're applying the whole of the aircraft onto that single point. Whereas if your target is so small, you can't have the whole aircraft hitting it. And the finite element analysis approach, we resolve all those issues, but the disadvantage, of course, you need to build the aircraft model and require verification, validation, and a lot of work needs to be done beforehand. Of course, once you build the model is there. You can use it again and again. And then in the aircraft impact analysis technique, again, I'm not going to go through into detail. There are 2 major parts. There are missile target interaction and load time function analysis. If I start with the load time function analysis, that is basically, I would say, the mainstream approach right now. Is mainstream approach, you build your aircraft model or radius function, you generate a load time function, you apply it to the structure as a pattern onto the structure. Easier, yes, and better computational wise, but of course, complex geometry will be a problem, or you would have discounted the disconnection or erosion of the aircraft, and fuel and debris, for example, is going to be difficult to capture. For missile target interaction, you have the benefit of all those, but a significant disadvantage of the modeling effort, and usually take a long time to run. It's okay to stick with the load time function approach, with the decouple approach, if you have a very large structure and very rigid, but that's not always the case. There will be some case where your target itself is small and is moving. This is an example. This is essentially a spent fuel cask that is put on the ground. You have spent fuel inside. If your target itself is moving, you have no other choice but using missile target interaction, because how can you do it otherwise? So this becomes the only reasonable option. So that is a very, very brief summary of the various different techniques and you can do. So now going to the detail of the research work that we are doing. As Richard was saying earlier, we started with understanding the different impact parameter sensitivity. So there are roughly three main kinds. One is what aircraft types. You might think, oh, that's simple. The bigger the aircraft, the better. But the problem is, the bigger the aircraft, you're putting much more into the cost and everything as well. This could be, and also the bigger aircraft may not always be the worst. And the other thing is the impact parameters. In this case would be your impact velocity, your impact angles, and things like that. And then your threat parameters, which is the parameters that are related to the threats itself. That would be your payloads. I'll go through them in detail later. But the overall approach is actually quite simple. Essentially what we do, we define what aircraft we need to look at. We define the parameters we need to bring forward for sensitivity analysis. We then set out a baseline and you construct the aircraft model. You undertake a series of finite element analysis, crushing them into rigid wall. You generate a series of load time functions and compare them. So the approach is very well known in terms of sensitivity study. It's just a lot of them. And then 6 aircraft were selected, and I go through one by one the reasons behind it. The first one is the Boeing 737. In this case, Boeing 737 together with A320, they are probably the most used aircraft in the UK for sure, and probably in the world. And your B767, which is unfortunately the aircraft being used in the September 11 event, and the Boeing 777, which is the largest twin-engine long-range aircraft. And then you have Airbus A380, which is of course the largest commercially available aircraft. In this case, it's 4 engines. And you have Gulfstream G650, which is a very large business jet, in this case, quite small. You're thinking, why? The reason business jet is it sits between a combat aircraft and a passenger aircraft, yet a business jet usually fly much higher velocity. And then, of course, you have the cargo version, a freight version of, in this case, we use a B767, but that could be anything. I mentioned earlier in the guidance, even various guidance provide you a different categorization of aircraft. So even within IAEA documents, in this case SR 87 and Tech Doc 1834, they have a slightly different grouping system. Then the next thing we need to do, of course, is model the aircraft. It's important that the aircraft is modeled properly. So we have a team build up this aircraft model, and then, hang on a second. So we have a team building this aircraft model, and it's important that the aircraft model is done correctly. So we then, the materials we're using, VTT testing results and MAPN test results to make sure the materials are used correct. We also only model what is needed to be modeled. So in this case, if you look at the picture on the top left corner, the wings are a lot smaller than you expect to see, because the non-stiff part, the flexible part, we don't model them because there's no impact to it. The nose, we don't model them because they would just crumble. And on the top right picture, all the seats and things we just smeared over the cross of the aircraft because it's not important what we're trying to do. However, the engines we model very carefully because that is the important part, the hard missiles. Also, you probably can't see the landing gear, also important part of it, which we model in a lot of detail. And then, of course, if you can always do some testing. Some people will have seen it already. And if you can do some testing, that's absolutely great, but I don't think anyone can do that. It's not, you can't do that in every single aircraft. So what other parameters then we then look at? Impact velocity. We know that's an important thing, so we need to look at. the impact angles, both from the horizontal and vertical perspective, the frictions, again, especially when aircraft hitting a rigid wall at an angle, the friction between the aircraft and the rigid wall is very important, and the mass distribution, I'll explain a bit later, and what kind of cargo they're carrying. So, of all these aircraft, we then work out 5 velocity per aircraft type. The starting velocity will be your landing velocity, landing speed, and then you then have the top one, which is your cruising speed. You then have 3 in the middle, so that gives you 5 data per aircraft. That will be good enough from our perspective to work out the trends and things. So we go through each of these aircraft, 6 of them, 5 velocities. We also look at horizontal impact angle. We pick up 4, 15, 30, 45, 60 horizontally, and vertically also 15, 30, 45, 60. But actually the vertical impact angle is not realistic, because ultimately any pilot or anyone who's an aircraft enthusiast will tell you anything above 15 degrees, the aircraft will have lost control. But we want a range. So in our case, we're actually doing what could potentially happen. So the aircraft could intentionally have a very high vertical angle. So we need to make sure we cover that. And frictions, typically 0.5 is used. But we want to see what are different if the frictions are different. For those who are involved in the negotiation or discussion with the ONR would know we sometimes argue with one single number for a very long time. Why is it 0.5? Why is it 0.4? And this is the idea, is trying to understand what are the impact and what we should be focusing on. We also look at the payload. You may not know, the way we define the weight of the aircraft, usually called MTOW, maximum takeoff weight. And you would be surprised, actually, you can't have the maximum payload and maximum fuel. If you have a maximum payload on the aircraft and maximum fuel on the aircraft, it will be above your maximum takeoff weight that the flight cannot take off. So it's always a proportion of a ratio balance between the payload and the fuel. So in this case, we look at a maximum payload with minimum, with whatever that remains for the fuel, and we have a maximum fuel with whatever remains that in the payload to actually understand what it means. We also look at the cargo configuration in this sense, again, because we know aircraft impact onto the structure, important is the hard missiles. So we need to know if it's not carrying passengers, but carrying big, heavy cargoes. So we look at 2 extremes. One extreme is a maintenance aircraft carrying engines. So there are 2 big engines inside the aircraft. You can't have more because it will over the payload requirement. And then you also carry the drill bits for the oil rigs, which is small, sharp cargoes. So basically after that, we do lots of series of analysis. In this case, 40 of them. Each of them take a couple of days to run. And then we compare the results. And as Richard was saying, we can't show you the detail of the results, but what we can show you is the key findings of what we found. The number one key finding that we found, actually, you would expect intuitively, if I want to create a maximum peak impact forces, I will have a normal impact directly to the wall. That's not always true. And we're a bit surprised at the time to find out. And then when we study the results in a bit more detail, we realize why. As I said, the hard missiles in the aircraft is the landing gear and the engine. So if I have a direct normal impact, I would have the landing gear hitting the wall first, and the effect of the landing gear would have gone before it hit to the engine. Whereas if a slight horizontal impact, at one point I would have both the engines and the landing gear hitting at the wall at the same time, creating maximum forces. This is actually independently verified by one of our, as Richard was saying, one of the peer reviewer in Germany. They actually identified identical results in this case. They were using Airbuses, but the results are very similar. But one thing we couldn't, we realized as well, is actually aircraft dependent. It's not every single aircraft the same because the configuration is slightly different. But actually, it's not too bad because once you slightly angle it, your area are bigger, therefore the pressure is actually less. So if you angle it slightly, in terms of pressure-wise, it's actually very similar to a normal impact. But it's something that we should consider that. The other one as well, which we think is quite important, is fuel configuration. We always debate what should be the payload, what should be the fuel. The maximum fuel configuration always the worst. That's what we found in our study. So we should really focus on that. And again, friction, there's no point discussing too much on friction because the effect of friction is very small. And same with cargo. There's not much different in terms of, in various different cargo configuration, you get slight peaks here and there, but ultimately in terms of forces, they are very similar. One thing we did found though is all the aircraft, if you compare the peak forces versus kinetic energy, what you then see actually is all the aircraft have very, very similar gradient with the exception of A380. Why A380? Multiple reasons. First of all, it's a 4-engine aircraft, and also the fuel configuration. In all the other aircraft, the fuel sits in the wings and those between the fuselages. The fuselage is between the wings. In A380, the fuel go all the way on the fuselage and the wings as well. They distribute much more evenly. And also, A380 have a much wider area of fuselage compared to the others. So even though A380 is over 150 ton heavier than the next big B777, for example, the actual peak forces are very, very similar. And it's actually the mass distribution is much smoother in this case as well. So these are all useful, important findings. But what does that mean? So we move on to the phase 2 of the work. In the phase 2 of the work, we know in phase 1, we improve our understanding already. So how do we use this information to improve our understanding? So we decided we want to look at statistical analysis. We want to see what's actually flying in the UK airspace, and then what can then help to recommend our recommendation to the ONR for them to decide what they want to do next. So we start by looking at the Civil Aviation Authority information. So we pick Civil Aviation Authority provide the takeoff and landing data for over 60 airports in here. So we have 1.7 million aircraft within a 1 year period. You're asking why 1 year? And I'm sure we all remember there is a COVID, unfortunately. So April 2022, what we found at the time is when the data becomes stable. So we have a 1 year period of stable data. And we also don't want to be too long a data because we want the data to be more than current. We only look at the commercial aircraft. In this case, we're ignoring the private jet, the official and the military aircraft in this case. And we also, but those are only flights taking off and landing in the UK. We also want the flights flying over UK. So we need to use another set of data, in this case a Sabra database. And this one have all the scheduled flights of 900 airlines worldwide, but it only contain the scheduled flights. It doesn't contain the unplanned flights or the ad hoc movement, etc. So the numbers are always slightly less than the CAA information, but it's very consistent. And also, overflights is quite important in this case because UK is very unique, and in the sense that UK sits between the Europe mainland and the America. So there's a lot of big flights, large flights that fly in from the Europe to America. They actually fly over UK airspace. So we need to include that. How do we do that? So we work out using a simple great circle routes of flights of the major airports on Middle East Europe to the Americas, and work out the flight path in this case. But we then remove those that is not relevant. So for example, the Spains, the Portugals and things are removed because they're never going to fly over UK. Same with the Scandinavias and things like that. So very much on the Central Europe. And then on the Middle East Airlines and the Indian Airlines, for example, because of the Great Circle route, actually they would fly over the North Pole. We haven't taken into account the war in Ukraine at the time, but it's a good enough representative, we think. So that actually have over 200,000 flights in there, big aircraft. So combining this aircraft, and to provide even more detail on this, we then weight adjusted this aircraft depending on where they are. So they could be full fuel at the beginning when they fly to America. When they got to UK airspace, the fuel would be how many percent used and things. So we worked that out as well. And then we put it in breakdowns of 50 tons. So from the picture you can see in a 1 year basis, there's over 1.1 million aircraft that is between 50 ton and 100 ton. That is very much your A320 and your B737. And then there's another big peaks in 150, 200 tons range. That's your B787, your A350 flights of that size. So what is that? If you put it into a distribution curve, that allows us to work out what is the mean. So the mean in this case from the maximum takeoff weight, as I said before, is the 737 and A320. A mean plus one standard deviation will be roughly around 220 ton. And that, the nearest aircraft in this case is B787, 800. And then a mean plus two standard deviations is actually just under 350 ton, and that's your B777. So this information is very useful in this case. Is statistical, but very useful that to help ONR to make the decision on that. So those are the two main aircraft that we say, Mr. ONR, you need to look into this. Because B787, that cover about 77% of the commercial aircraft on the UK airspace. And the B777 cover 93.5%. This is much larger than other countries in that sense because of the location of the UK airspace. And we then need to look at one thing we did found, if you look at this, both these aircraft are twin engine. So there's no four engines aircraft in here. So are we missing something? So we want to look at the trends in there. What are the typical four engine aircraft? They are the A380, they are the A340s, and the B747, of course. We look at it in the last 10 years, the number of four engine aircraft actually reduced quite significantly. Main simple reason being four engine aircraft is a lot less fuel efficient compared to a two engine aircraft. So the trends moving forward is very much on a wide body twin engine aircraft, which is exactly what we found, we're happy with that. Also, we found out that the trend is very much moving from the classical aluminium into a composite material. But actually it doesn't matter from our perspective. Composite material, all we're interested in is mass impact onto the structure. We also look at what are the future trends in the aviation right now. Sustainable aviation fuel is definitely one thing that is being talked about a lot. Happy about it, but really in our perspective doesn't change anything. Also, the flying taxis is very popular. Boeing is developing something. I think XPeng in China is doing something else. Singapore is doing something else. But again, they're small and doesn't impact us directly. Hydrogen-powered aircraft, that's being pushed for as well. But the earliest not going to appear until 2035. That is a very optimistic guess, really. So we are quite confident that nothing will change. The study we've done, nothing will change in the next 10 years or so. So what does that mean then? So now we've done phase one work. We know statistically what it is. So we provide all this information to the ONR, and we want to understand, based on current and based on future, what we want to do with it. So as Richard was saying, a lot of information is sensitive, but the duty holder, if they want to, they can have the proper path to get those information. So what we then do is we use the new threats and the existing threats. We do some consequential analysis. We pick three typical structures. One is big reinforced concrete flat walls, and then cylindrical walls, and also a dome structure. These are very typical reactor-type constructions. We then do some missile-target interaction study on those and compare the results from the rotation perspective, from the strains and the reinforcement perspective, and various different things. So I spent almost 40 minutes talking about various different tests. So where are we now then? So how certain are we from the aircraft impact hazards? I would say we're better than before. What we've learned is we definitely have better understanding on what is important, what is the big ticket item that we should be looking at in terms of the impact and threat parameters. We also have much better idea of what is actually flying in our UK airspace, and we think the information is valid for a while. We're definitely more confident, and therefore, from assessment perspective, from the ONR perspective, we're happy. However, as we say, we're all humans, and grazing into the crystal ball is very hard. And human factors cannot be predicted. But what's next? So the future work is still being discussed, what will happen next. But what we think likely to happen is, borrowing from the seismic world, so far everything, the log time functions that we generated are deterministic. So because of all the data we now have, it is possible for us to move into the probabilistic space, just like seismic, PSHA, for example. So we could potentially generate log time functions based on 84% high confidence, low probability level. So this is the area that we want to move into, and this is the area so far in the aircraft impact field that haven't been moved into, simply because it doesn't have this set of data, and we think we're getting there. And as Richard was saying earlier, we have peer reviewers from Arabs. One of them is actually sitting there. And also we have Wilfeld from Germany. They are one of the very consultants that do a lot of work in this area in Europe. And thank you for the work. I think that's it from here, actually. Thank you.
Thank you, Ming and Richard, for the excellent presentation. I think we have, and you're on time as well, so we have time to take questions. There is a question from online. It's just asking, is it possible to have a copy of the presentation? I mean, you can answer it now, or we can say we can get back to them later. Whatever you want to respond to that.
Yeah, we'll get back later, but there's no reason why we can't.
Okay.
Yeah.
So that's the only question I have from online. I'll open it to the floor now. And Ian, if you please introduce yourself. Everybody knows you, so. So you.
Microphones or we shout
There is a, yes, there is a microphone. Yes.
I don't think they're turned on.
I think they are. They're normally the
okay.
technician makes sure they're on.
Right.
Does that work?
Yes.
Yep. Great. So Ian Smith from Atkins. Thanks, Richard, for letting this happen and the ONR funding this sort of work, because it's so essential. And Ming, thanks for a great update. I can't help the aircraft that I'm familiar with is the F-111 in what's ASCE 58. Very old document, and if you look at it, it's all about blacktop. Because the ASC number 58 has been reused, but the previous one was all about the design of nuclear facilities. And it's a fantastic book if you can get hold of a copy of it, with the background, the historic background to all this. But what was great about the F-111 was the forced time, sort of historic mathematics, if you like, all the way back to our real history a few hundred years ago. It's all about the change of momentum. And I was interested that your incisive work that you're doing now is in far more detail. But as a benchmark, the rate of change of momentum is a very easy thing to do. And the F-111 had similar graphs that when you got to the engine, it rocketed up the actual force and then down again. You obviously know so much more. But as a benchmark, is that still a useful useful measure, just the change in momentum. I understand what you said about breaking up and bits landing in other places, but the fundamental mechanics that we all learned from Newton's laws and everything is still there, isn't it?
It's not that different. I
Yeah.
think what Reyes did is on top of that, he considered the crushing zones.
Yes.
It's not just a pure change of momentum.
Yeah.
That is what Reyes have is like groundbreaking at the time to come up with this information or this idea of the the crushing zones. So nothing wrong with what done there, but there are more that can be done, which
Absolutely.
is the 1960s Reyes function.
Yeah.
What we've done now is one step forward, but the physics remains the same,
Yeah, exactly.
which is the great thing about it.
And thank you for sharing all that, because I know it's complex. I did have another question, but I just checked it out with Richard and we'll leave it. Great, thank you very much. And it was very interesting and very timely, because we've spoken about this before historically, and you've done a previous talk.
Yes.
And this is so much more interesting because it's all moved on so much more. So thank you very much.
Thank you.
Paul Doyle Jacobs. The question we're all very much interested in is when are we going to see this published by ONR? And the other second part to that is in what form are we going to get published? Is it going to be a sort of prescriptive force time curve, or is it going to be a sort of much more generic information?
I think in terms of the publishing, the research, any ONR research, it's one of our big things to make it publicly available. It's one of the, from the Energy Act, it comes right from there. So we want to publish everything we can. We have got to be careful how much of the report content is on the website. That's got to be carefully scrutinised. But duty holders will be able to contact us, and provided they've got the relevant security protocols for handling the information, they should be able to access all of the research of those reports. And that'll be people, not just me, who'll have to deal with that handling of the information. So that's one side of it in terms of the actual data of the research. In terms of the ONR position, I mean, traditionally that's always been an expectations letter, just outlining very clearly the different parameters and other bits of guidance relating to how the threat is characterised and handled. There's no plans to change away from that, still be the same. The difference is that this is now going to allow us to just refresh and revalidate that expectations letter. And again, that's something which we will be communicating with duty holders on, and in fact on some of the new build areas we've already done that with some of the duty holders due to where they are with their programs. We've had to sort of accelerate that process. So I think that answers your question, Paul. Sort of the plan.
Yeah.
So you should, I think, if you're from a duty holder perspective, you should be able to access everything. It might take a bit of time to cross all the I's and dot the T's to get there, but that's the intention.
I was just wondering if you're intending to sort of push forward a design force time curve, or is it going to be left to
No,
each duty holder to work out from the data what to use?
the purpose of this work was to inform to what extent our existing threat definitions actually need to change. To be fair, we did have those conversations, but it was felt that to go to that of actually specifying load time functions is that it really heads us down a very prescriptive route, which we didn't think was wise. Yeah.
Right, thank you, Richard.
There is a question online very much similar, which says, have you published in any peer-reviewed journals?
No, the answer's no. The answer's no. And again, it comes back to that response before, to what degree we can or are able to. I think we'll need to carefully consider. None of this is particularly easy given the topic.
Okay, we can take a question from the room.
Could I just say in that last one, what we're experiencing is a great interest in the topic, because it is so fascinating.
Yes.
The computational interest is there, but there's obviously the other side of the argument as well.
Yes.
But,
Thank you very much for your presentation. Vipul from Mott. My question is related to one of the slides where it was shown that the fuel-rich case is slightly more onerous for the impact assessment. Were there any considerations for the cases where a military fuel aircraft is going to impact a nuclear structure, like a fuel tankers? So, like you have Boeing KC-130, which is a Boeing 767.
The simple answer is no. It's not been done, but it's not been considered. One of the main criteria of selecting the aircraft is aircraft that is possible to be hijacked or reasonably expected that could be hijacked. Well, you know what I mean. And so to get to that position for that type of aircraft we consider is very, very difficult. Yeah.
Thank you.
Thanks. I will pick up a question from online which says, comparing the uncertainties of the impactor with the uncertainties of the nonlinear modeling of the resistance, what is your opinion about the bigger influence on the overall results?
That's a good question.
This is from Wondrel Pere.
This is therefore the title of the presentation. How certain are we? We're not very certain. We are more certain than before, but we're still not very certain. I think it's a simple answer. But every work we're doing, we're getting to that position that we're more certain. But ultimately, as I said in the last slide, it's human nature. Yeah.
Yep. So thanks, Ian. Sorry.
I know.
Hello, Joanna Playbill from Atkins. If we say look 20 years down the line and the trends are very different with respect to the planes and so on, how would we be able to do a stress test and make sure that the whole structure is up to code and it can still stand if the patterns are different, the planes are different, the forces are different and so on? How would the ONR handle that?
I mean, looking ahead, especially for new build, I suppose you could use the term future-proofing to some extent. It's always challenging. Probably is very challenging in this area to try and predict where things could be. But one thing we always have is our 10-yearly or periodic safety review. So, I mean, right at the outset, you can only go so far with how you can predict. And after that, should things change outside of your predictions, then essentially that would need to be picked up in those periodic reviews of safety, which are typically conducted every 10 years. And if there was something which had suddenly come out which was different, then that would need to be reviewed on its own merits during that process. It would be the best answer I could give.
There is a thanks. There is a question online which is more about analysis time. So I think you mentioned you run up to 40 analysis.
Yep.
How long does it take? 1 day, 2 days, 3 days?
Depends. It range between 1 to 3 days. So roughly around 2 days each. Yeah.
We can take a question from the room.
Yeah.
I'll go for another one. Oh, is it? Yeah.
Well done, Ian.
Oh, yes.
Feel sorry.
Exactly.
Who was there?
Yeah.
Conrad Isaac, representing Arup. As one of the peer reviewers of the work, I just first of all like to say that there's a lot of really good stuff that's been done, and it's providing great technical underpinning to a lot of the parameters and the importance and emphasis placed on those parameters for the work that's carried out. I suppose my question would be, you were talking about moving towards a probabilistic basis. Just like to understand what would be the data for the probabilistic analysis that would be carried out in order to determine the parameters of the impact.
We haven't taken it to properly yet, but the idea very much is the aircraft mass, aircraft impact velocity, the angles, all these itself can be a set of datas with means and standard deviations. So with these informations, you could actually do a fragility analysis, which then give you a set of load time functions of certainty level. So technically speaking, we could come up with a Boeing 737 of 90% confidence level. The load time function could be similar to that of a B787 of 50% confidence level. That actually the same. The beauty of having a probabilistic study in this sense, if there is a requesting party, say SMRs or AMRs, that they have done some work in a different country, they come into the UK, they're using a different type of aircraft that is not the same as the expectation in the UK. So how do you then fit into the UK regulatory regime? So if they have done, say, a deterministic study of an aircraft that is not similar to the UK, but you can then compare that probabilistically into a load time function that's expected in the UK at a certain level, you can then make an informed judgment of what that means. That is the idea behind it. The details haven't been worked out yet, but I personally feel strongly that that is the area that we should be moving towards, or else you end up have to redo that every time you move to a different country. So that is the benefit of it. Yeah.
Thank you. I'm just going to take a question from online. There's lots of questions online. Online is buzzing at the moment. And in fact, there's many questions asking when is this guidance going to be published. So that's a common theme. But this one picks up. Can you mention to structural engineers acceptance criteria when designing for a direct impact of an aircraft to the nuclear dome? So I think the question is, can you mention
Yes,
to structural engineering acceptance criteria?
That is very much, I think, on one of the slides I was talking about how your aircraft impact safety case is built up. You could be any acceptance criteria, to be quite frank. If your aircraft impact safety case strategy is fine. If I said my reactor can have a direct impact and still works, I don't need anything. So that's the extreme, of course, but majority of it will be relies upon on NEI 0713, which will typically will say something like your integrity of a containment remain intact, or your reactor cooling remain in place. Same thing with the spent fuel pool remain intact, or the spent fuel pool can be cooled after the event, or and can be remain. So that is the classic performance requirement. And to achieve that, if, say for example, my reactor and my spent fuel pool are both in the reactor dome, as an extreme example, then I could just say my reactor dome would therefore remain intact and have no scabbing at the concrete at the inner face, because what that means is there's no missiles from the concrete hitting the reactor or the spent fuel pool, and that would be a easier option to do that. Or you could say, I would like to go into more detail. In IAEA term will be a design extended condition 2, that my concrete can actually breaks and things falling into, but my cooling system and the reactors will have designed for this sort of missiles. So it very much depends on how the safety case is built up. It's not a simple answer. Yeah.
We can take a question here from the room. Yeah.
Hello, Alex Carroll from EDF. First, I want to thank you for carrying out this important work. As we all know, it had been quite some time since the previous standards had evolved, and those are the standards that we had taken into account. So thanks for that, and I look forward very much to receiving the report in due course and having a good read through it. So that will be very interesting. I think that previously it would have been legitimate to ask whether those standards and the previous analysis led us towards a bounding case. And I think that the question I have is, how much more certain are you now, with the updated analysis that you could define a bounding case if indeed that is the approach you wanted to take?
I mean, I think we need to be careful with the word bounding, because I mean, the whole premise of assessing this hazard is it's on a best estimate basis. It lies within that beyond design basis area in the way it's considered. So we're not looking to produce threat definitions that are bounding. We'd end up with something which is, we couldn't build or live with, really. So the key thing about this was testing whether what we've got is representative given what we know now. So there was no way around, really. We really needed to do an exercise like this to test the validity of not only what was flying, but also how we represent that impact and that missile. And that has highlighted things for us to think about. So I think in a roundabout way answers your question. So yeah, we're not looking to try and produce something which is always bounding, because it's that goes against the philosophy of how this hazard is assessed, or our expectations of how it's assessed.
So you have more confidence that that your understanding is representative now?
Well, that would be correct. So now we've come away with thinking, actually, we've got a little bit of tweaking to do here. We've actually got the reasons why, and we know how significant they are to inform that why, and now we can do those tweaks. Whereas I think if we go back to post 9/11, although that thinking had been done, we didn't have this kind of evidential basis to inform it, which we have now. So I think we're going to be in a much more informed position going forward.
Thank you. There's, as I said, online is buzzing. There are lots of questions online. We just asked the question, did you vary the modeling parameters of nonlinear concrete structure modeling? That is, did you consider any strain rate effects of concrete? Can you point out some critical aspects of the modeling of the target structure?
I have to pass it to our team.
I know.
On that. It's too detailed for me to answer, unfortunately.
You have somebody.
No.
Oh, okay.
Okay.
Yeah.
Hi, Alan Ninjuela from Mott, MacDonald. I had a question in terms of the materials. Has there been considerations on future materials or low carbon concretes and everything else?
Not in terms of concrete. The consideration of materials all about aluminiums and composites. So we're focusing on the aircraft, not on the target, should we say? Yeah.
Thank you.
But ultimately, that is a duty holder responsibility. Yeah.
Colin Morrison, Colmore Consulting. Really, I think a question to Richard. From, if you want the experience of 9/11, it isn't just the aircraft impact, particularly when they're saying the fuel load is high. Are you looking at combinations of impact and fire on the target? Or are you thinking about putting that forward to the duty holders?
I mean, that's typically always considered, the risk of fire and other things. I mean, the global effects and the vibration and sort of the dynamic effects of that impact on plant and equipment, and then going back round that fault analysis route to test whether your strategy is still valid. So that's all. None of that is being touched. That's all still remains. Yeah.
Okay, but I think the thing we learnt there is just what a fuel load can do as a parallel threat.
Yes, this has always been considered. Yeah. Aviation fuel, fireballs, pool fire. Yeah.
I have questions online, but if there's any from the room, or let me just pick up an online question and then we can. This is from Andy Mayer. He says, where the fuel load is high, the consequence of the resulting fire on the nuclear inventory could be more severe than the initial impact. The fuel can soak into the ground and provide a reservoir of fuel to feed a fire over an extended period. Has your study considered this hazard?
Not in this study specifically, but that is something that being considered in when you look at aircraft impact as a hazard. Yeah.
Okay, thank you.
So Ian Smith of Atkins, again, sorry. This gentleman mentioned about the fuel tanks being quite a key issue. Is it that if you have a liquid in a closed cell, the initial impact can be very severe because it's a pressurised container, it can take a pressure, therefore you're getting a very significant inertial bang at the beginning, but as soon as that fractures, then it's a fluid with no shear strength, so it's a different material altogether. It's still significant, that initial bit.
Yeah, you're absolutely correct. I think one thing I didn't mention in the slide, we probably should have, is because we're doing a lot of analysis, we have to simplify things.
Absolutely.
In an ideal world, what we would have done, we have modeled the fuel as SPH element. That is how, if we want to do a final big analysis, we would have used SPH element to model the fuel. But because we're doing a lot of analysis, in this case, we just use fixed masses into it. So, but you are completely right.
Yeah.
The initial impact of an SPH element and a fixed mass of fuel will be the same, but the subsequent effect will be completely different.
Yeah. Thanks, Ming.
Yeah.
That's great.
The next question is particularly for Richard, I think. It says, what is the regulator's expectation of the plant condition to be considered in the design for the most frequently flown aircraft, the B787 and B777? Is it a design extended condition? What type of aircraft should be considered for design basis condition? And then there is a second part as well. Maybe you answer that.
I mean, it's a good question because it starts to reinforce that if I were to answer some of those things, it starts to articulate what our UK threat position actually is, which I cannot do. The one thing I will say with some of that is that on some of these things, there is opportunity to form a conclusion based on discussion with the duty holder. Okay, so some of these are not cut and dry. There's different ways that we can represent some of these parameters. And those are the sorts of discussions that do go on in determining a final threat position. So hopefully that helps that question.
I could add a bit more to that without compromising the security issues. As Richard was saying earlier, there are two scenarios we're looking at: malicious and accidental. That information about the statistical analysis is very relevant to the accidental aircraft impact. That information helps on determining what the malicious aircraft impact is, but it's not the final answer. Right? But for accidental aircraft impact, that is important. And accidental aircraft impact, depending on the frequency of occurrence, it could be a design basis. It could be a beyond design basis, that purely based on the probability of occurrence. Yeah.
Any questions? Any other questions from the room?
Yeah, second question, if I may. I was interested in the way that you, treated the data that you obtained on movements, and also what you said about the malicious case. Considering the accessibility aspect. So in the accidental case, if you wanted to, you could potentially consider the extent to which emergencies become, consequences that we were interested in, or, as is mercifully the case in the majority of, emergencies, they end relatively calmly, on an airfield, and that's always going to be the first priority in those cases. Is there? I don't think that's something that you've necessarily taken into account, but is it something that you could potentially consider, to refine your understanding of accidental cases?
We've had lots of discussions about human elements, essentially, is where this goes. And that starts to become very tricky because it's humans, and sometimes the behaviour is not easy to predict. So this study is very much focused on the areas which we can throw some analytics out. We can do some statistics. So trying to do the things we can do with the data, let's do them well, and actually have them presented in a way we can do it. It doesn't take away from the point that you mentioned, and those accessibility, these other things are important factors, but how you were to then characterise those things starts to become very, very difficult, and we have discussed it, but the method to actually deal with those in some quantitative way is not something which we've addressed at all. That helps.
Thanks.
There is an online question from Chris Evans. Is there any consideration of potential hypersonic missiles now being introduced by the military? Would this be considered as a very low probability beyond design basis situation?
We cannot discuss that.
I can't really comment on that, to be honest. Yeah. Park that one.
Okay. So any more questions from the room? Any comments? Paul?
For the accidental case, you've talked quite extensively about the overflying of aircraft in the UK, etc. Did you bring that together with the statistics on aircraft actually failing? Because on modern statistics, very few aircraft are failing.
Yeah. Simple answer is no, but as you already said, very, very few aircraft is failing. So you could almost say that the frequency of failings is the same, so it doesn't really matter in that sort of probabilistic sense, if you know what I mean. But when you work out, there is actually a separate, quite a detailed approach to work out accidental aircraft impact. What we're showing just now is statistical sense, what are the likely aircraft that, in terms of mean and mean plus standard deviation, etc., there is actually not a codified approach, there's a guidance that is quite clearly defined to work out your accidental aircraft frequencies. You can break it down into 5 different categories of aircraft and different weights and things. There are specific approach to do that. So it's not part of this study, but there is a separate work guidance that's actually, in fact, the Annex D in Tech 13 actually briefly mentioned that as well.
Yeah, Annex 4.
Good evening, Francesco Monfuni from Nuclear Generation. Thank you both, it was really interesting presentation. It was just a curiosity rather than a questions for Richard, if possible, if you can answer. Do you force, link to one of the comments that Dr. Ming raised on, for example, developers that could have done a design in another country and then moving into the UK for applications. Are you expecting that any parts of these studies may be shared between the ONR and other regulatory offices in other countries, just to check, let's say, if the level of analysis is comparable or if you're far off from one country compared to another?
It'd be interesting, wouldn't it?
Yeah.
Very useful. Unfortunately, it's just not that easy to do. Threat definitions from other countries are not available, or are very tightly controlled, quite rightly. So no, that's not easy. That's not easy to do.
I appreciate that.
It's the simplest answer.
I think we have, there's still questions online, you can have a look. But I think we've taken most of them. The online room has been buzzing, and so has been this room. I think it now leaves me to thank the speakers for giving us such an interesting presentation with lots of questions. And I really enjoyed chairing this session. So let's thank them once again. I wanted to mention something for the young our YMS, their committee, new committee member there. I think the deadline for new submission is up to 30th of September, right? So if you are considering joining SECED, you'll find all the details in our LinkedIn page. Please do consider joining the young. We have a very active young members SECED committee, and they are very active, organize lots of events. So please do, if you like what we are doing, please do consider joining them and get your applications by 30th. Thank you, and we look forward to seeing you for the next event that will happen in October, which is the AGM of the Young Members Committee. Thank you very much.